So here in video 2, we're going to talk about some of the rules of probability. Now, these should sound pretty familiar, at least several of them should, because from your algebra class, because these are many of the rules that we learned in algebra when we're applying algebraic concepts and principles. So the complement rule says that the probability of a complement, remember the complement is everything that is not everything in the sample space but our particular event, is equal to 1 minus the probability of the event. So when we were looking at the example in the last video of the snowboarder winning the gold medal, if winning the gold medal is event A, then the complement of event A is anything but winning the gold medal. So the probability of the complement is 1, remember 100% essentially, minus the probability of winning the gold medal. So the addition rule allows us to find the probability of the union of two events. And remember, the union of two events is an or. So what is the probability that A or B is going to occur? So let's look at this rule using a Venn diagram. So remember, a union is that A occurs or B occurs, right? So if we're trying to calculate the probability of A or B, we don't want to simply add the probability of A and the probability of B because that's going to double count the area of the intersection where both of them are occurring. So what we want to do is to take out that intersection. Remember, the upside down U means intersection, and the right side up U means union, right? So the probability of the union of A and B is the probability of A plus the probability of B minus this intersection of A and B. And so that tells us the probability that one of the two is going to occur, or both, but looking at the probability of both without taking into account that intersection. Now, if we have two mutually exclusive events, remember mutually exclusive means that if one occurs, the other can't, right? So if A occurs, B can't. If B occurs, A cannot possibly occur. So then that means that both of them cannot occur. So that means the intersection is 0. They don't overlap. You can't have both. But you can still have the union because that is saying A occurs or B occurs. So in this case, when the two items are mutually exclusive, then the probability of the union of A and B is the probability of A plus the probability of B. Now, really, this is the same formula that we looked at before. It's just that because the intersection is 0, this formula is really the probability of A plus the probability of B minus 0, because we subtract out that intersection. But since the intersection is 0 when we have mutually exclusive events, then that's just subtracting 0 at the end, so we can leave it off. So here we have an example. We're told that the chance of joining, this is for a particular student upon graduation, and she has decided that her chances of joining the Peace Corps upon graduation is 25%, and the chance of going to law school is 35%. Now, these two events are mutually exclusive because if she joins the Peace Corps, she's not going to law school, at least not immediately out of high school or out of college. And if she goes to law school, she's not joining the Peace Corps. So the probability of doing one or the other, of joining the Peace Corps or going to law school, is the Peace Corps 25% plus the probability of going to law school of 35%. So we could add those together and say the probability, the union, the probability of doing one or the other is them adding together. Because they are mutually exclusive, there's no overlap. You can't do both at the same time. So the probability of doing neither then is the complement to the union of A and B. And so that would be 1 minus the probability of joining the Peace Corps or going to law school, or 40%, or zero point 0.4. So in business, the probability of something happening is oftentimes conditional on the probability of something else happening, or at least if something else happens, the probability changes. So for example, the probability of finding a job out after college, we would call the probability of A. But we know that the probability of finding a job is greater if you have prior job experience. So we'll call probability B the probability of having prior work experience. So a conditional probability is written as given that. So for example, this line here, this bar, reads given that. So the probability of A given B means the probability of finding a job given prior work experience. So that's going to be different than just the probability of finding a job, because prior work experience exerts some influence over your probability of finding a job. So our union of A and B says that if B has occurred, so if we have prior work experience, then the sample space reduces to just B. So if you have work experience, then your probability of finding a job would just as here, because you're not going to find a job without work experience if you have work experience. So that is conditional on having work experience. So given two events, with each having a positive probability of occurring, we would say the probability of A given B is equal to the probability of the intersection of A and B divided by the probability of B. Now, we could write that the other way. We could say the probability of B given A is the probability of the intersection of A and B divided by the probability of A. Now, in our example of work experience, that doesn't really work. You can't say, well, what's the probability of having work experience given that you found a job? That doesn't make sense in that scenario. So it would only work in that scenario, the probability of A given B. But there are certain scenarios where it could go either way, right? So here we're told that an economist predicts there's a 60% chance that the country will not do well economically, and a 60% chance that country A, will not do very well economically, and a 25% chance that country B will do poorly. There's a 16% chance that both countries will do badly. So what is the probability that A performs poorly given that B performs poorly? So here we've written out the probability of A performing poorly is 60%, the probability of B performing poorly is 25%, and the probability of both, of the intersection of A and B, is 16%. So if we're looking at the probability of A given B, then we would take the probability of the intersection of A and B divided by the probability of B. Okay, so the key here, remember, is that your denominator is always the probability of your given that. Okay, so if it was the probability of B performing poorly given A performing poorly, then we would swap the denominators there. So a lot of times we want to see if two events influence each other. So we're going to say the events are independent if the occurrence of one does not affect the occurrence of another. They are dependent if the occurrence of one is related to the probability of the occurrence of another. So how interrelated are these things? So if we're talking about economies, if one country's economy does bad, is that going to influence other countries' economies? Are those independent or dependent? So if they are independent, then the probability of A given B is just the probability of A, or the probability of B given A is just the probability of B, because they don't influence each other. So there's no, the probability given something else happening isn't relevant in this scenario. So for example, we're told there's a 2% chance a desktop computer will crash, a 6% chance a laptop will crash, and a 0.12% that both will crash. So are they independent? What do you think? So if we say the probability of the desktop crashing is D and the probability of the laptop crashing is L, then the probability of D given L is the probability of the intersection, or both the desktop and the laptop crashing, divided by the probability of the laptop, which gives us 0.02. So in other words, if this is very, very small. So the probability of your desktop crashing does not affect the probability of your laptop crashing. If we look at it the other way, what's the probability of your laptop crashing given that your desktop crashes? It's slightly larger at 0.06, but still really small. So we would conclude that these events are independent, right? And if we think about it logically, it makes sense. Your desktop crashing doesn't have any effect on whether your laptop crashes. If they both happen to crash, I mean, that's unfortunate, but it doesn't make sense that one would really influence the other. So again, part of this is we need to use some of our logic in there as well. So the multiplication rule says the probability that A and B both occur, so the intersection of A and B, is the probability of A given B multiplied by the probability of B, or the probability of B given A multiplied by the probability of A. Now, keep in mind that when two events are mutually exclusive, then that intersection is 0. Right? So if the events are independent, then the probability that A and B both occur is just the probability of A multiplied by the probability of B. So let's look at another scenario here. So the CFA is the Chartered Financial Analyst exam, and we're told the probability of John passing is 0.5. And the probability of Linda passing is 0.8. So first of all, are these events independent? Is the probability of John passing affected by or conditional on Linda passing, or is the probability of Linda passing affected or conditional on John passing? What do you think? So let's look. What is the probability that both pass? Well, if we assume that these are independent events, that John and Linda's percentages, probabilities of passing are not related, then we can just multiply the probability of John passing and the probability of Linda passing together. And so we get the probability of 0.4. So there's a 0.4 or 40% probability that both John and Linda will pass. So what is the probability that at least one of them passes? So then we would look at the probability of the union. So remember, that's the probability of John passing plus the probability of Linda passing minus the probability that they would both pass. So here we get John of 0.5, Linda of 0.8, add those together, subtract that probability that they're both going to pass, and we have a 90% probability that at least one will pass.